Hi, I'm video analysis specialist and biomechanical engineer, and today we continue diving into this paper. So let's get started. Analysis of joint moments are important in the study of human motion, as joint moments correspond to resultant muscle forces and loading of passive structures. So this sentence emphasizes the biomechanical relevance of joint moment. They reflect the net effect of muscles contractions and passive tissue responses. Ligaments, for example, it's foundational reason why joint moments are central to study movement and injury mechanisms, especially ACA-related loading. The joint moments are usually calculated using inverse dynamics on force plate, recording the marker position data from infrared camera system. This describes the standard lab-based setup motion capture system like Vicon, Qualisys, or BTS by engineering or gate lab track markers to gate kinematics, while force plates measure external forces. And inverse dynamics uses Newton-Euler equations to back calculate joint torques or moments from these inputs. Next, there is a need to low-pass filter position data to remove random noise, especially because errors are amplified when differentiating position data for calculated segment inertia for inverse dynamics. Differentiating position data to get velocity, then acceleration, increases noise dramatically. Filtering remove this high frequency noise, especially critical because acceleration is multiplied by mass and distance in the moment equations, making errors propagate heavily. Next, position data is typically filtered with 5 up to 20 Hz cutoff frequency based on the frequency content of normal movement and the errors. The cutoff range aligns with human motion frequencies, usually under 10 Hz, and filtering above 20 Hz may retain noise, while below 5 Hz could attenuate actual moments, motion signals. And it's balance between preserving motion and eliminating noise. Next, force platform data, on the other hand, is considered accurate and with less need of filtering, as force data is not differentiated in the inverse dynamic procedure. Since raw force data, for example, ground reaction force, is used directly without derivatives, it contains less cumulative noise, so it is typically doesn't require aggressive filtering, and still very high frequency noise, for example from heel strikes, might require filtering, mild filtering. However, concern has been raised for possible artifacts when using different cutoff frequencies for force and position data in inverse dynamics, especially for high impact movements, typically analyzed in performance and sport injury biomechanics. This is a critical problem in inverse dynamics. Inconsistent filtering leads to mismatch in data alignment. And for example, if the force signal retains sharp impact peaks but kinematics data is too smooth, the distort calculated joint moments product in artifacts not present in real motion. With high intensity movements like running and jumping, peaks in ground reaction force and segment acceleration are seen shortly after ground contact. In such exposure actions, the biomechanics are characterized by sharp, high amplitude transients. And capturing these peaks correctly is crucial for analyzing joint loading and understanding injury risks like ACL ruptures. With a high cut-off frequency for force and low cut-off frequency for movement data, impact peaks are retained only in external forces but not in segment acceleration. This explains the core artifact mechanism. The force plate captures true spikes, but the kinematic data, over-filtered, show smooth accelerations, which leads to a mismatch in dynamics, essentially fake joint moments patterns. This inconsistency within the equations of motion will give rise to artifacts in the joint moment curves at the acceleration of the segments with no correspond to the measured ground reaction force. Inverse dynamics assumes accurate matching between forces and acceleration. If that's validity, the resulting joint moments are biomechanically invalid for injury prevention or performance assessment. Such artifacts can lead to wrong conclusions. This can be exemplified by an analysis of knee moments in jumping. The knee is often used as a model joint because of its complexity and centrality in sport injury. And it also experienced large dynamic loads, making it a prime candidate for artifact sensitivity analysis. A study on job jumps from 30 centimeters analyzed using accelerometers found the peak tibial acceleration to be 15 and 8 g. This quantified their intensity. 15 and 8 g is enormous acceleration, showing how real motion includes rapid spikes. Filtering out these spikes in kinematic data while keeping them in force data leads to significant calculations errors in joint moment estimation. So thank you very much for watching. Follow me for new videos. Have a good day.